the example that I'm giving you is, of course, one that clearly it should be obvious that we routinely are going to solve the question whether this grammar G sub 0 generates exactly the same, generates the same grammar language as the original grammar G sub L. So how does one go about that, inasmuch as the equivalence of context-free grammars is undecidable? Well, we can, in fact, do simpler things. This is a general problem, accepting two arbitrary context-free grammars and determining whether they generate the same language. We can go and verify for each of those local modifications, which are, of course, much simpler, that they, in fact, do not change the language that this grammar generates. The resulting grammar generates, and so we do that for G1, and then based on that for G2, and then based on that for G3, and so on. So after 24 of these verifications, we then end up with G0, and we've verified for each of them that, in fact, it generates the same thing as G sub L, and therefore G sub 0 also generates the same thing as G sub L. But the more elegant and more straightforward approach, namely that we first do all the modifications, and in the end we do one verification step, which takes both the original grammar G sub L and the final resulting grammar of all the modifications G sub 0 and verifies that they're equivalent. That is not possible. So what that means is that in this particular case, it is futile to expect an answer to, in this case, for the equivalence of context-free grammars. There is not any such thing. And it is important for you to understand that if a problem has been found undecidable, this is the end of that. There is nothing, no amount of intelligence, no amount of industriousness, no amount of brilliant ideas is going to change that outcome. This is undecidable today, it will be undecidable tomorrow, it will be undecidable in 1,000,000 years. Nothing will change. Once a problem has been found undecidable, it will remain undecidable, and there's absolutely nothing anybody can do about it. So in this particular case, if you have a problem that you want to solve, and, well, typically the process is that you try to solve it and you fail miserably over a long period of time, and eventually then you start looking, well, maybe this problem is undecidable. And if you then actually determine that it is undecidable, then you have really two possibilities. Either you throw up your hands and say, well, that's just it, or you try to determine a sub-problem. Remember, I said that this is a property of a problem. It is not a property of an instance. An instance of a problem can, even if the problem in and by itself is undecidable, you probably will be able to find a solution for that instance. In fact, what typically happens is that if this is your complete set of instances, there's only a small subgroup of evil instances that render the problem undecidable. The other problems may well be solvable. In this particular case, for instance, the individual local modifications of the context-free grammars that we're dealing with are typically doable. This is not a general problem of the equivalence. This is simply looking at productions and how they're modified, and then verifying directly that the new what the new productions generate is exactly the same as what the old productions generate. So from that point of view, in many cases, the vast majority of the instances are in fact doable. It's just the entire problem, which of course contains those evil instances, they render the problem undecidable. So, as I said, either you throw up your hands and say, I can't solve it, which is typically not particularly attractive. I've always argued that undecidability is the ultimate un-Americanness, because if you say, well, I can't do something, then most people will say, well, either you're too lazy or too stupid or both. In this particular case, it has absolutely nothing to do with laziness or stupidity. It has to do with the fact that the problem is undecidable. And no amount of blood, sweat, or tears is going to change that. You will not be able to come up with an algorithm that solves an undecidable problem. So that's the basic story, and the only possibility is that you may have dealt with something that was too general. That was, of course, the situation of the equivalence of context-free grammars. We basically have some sequence of local modifications, each of which is probably verifiable. But instead of doing that, we invoked a general problem, namely determining whether two context-free grammars generate the same language, and that turned out to be undecidable. And so in many cases, if you run into an undecidable problem, it may well have to do with the fact that you are doing something in too general a form. If you stick to small steps, baby steps, then it is much more likely that you will be able to do things. But if you want to do huge steps, then that may not be a feasible way. So that is undecidability, and now we're talking about infeasibility. Well, infeasibility basically says, well, we can solve it, there's an algorithm, except it has a time complexity that is prohibitive. So typically, if you have a time complexity that is exponential, so n is the size of your input, and you have time complexity that is 2 to the n, that means that what you are dealing with is a problem that has a complexity that guarantees that you will not be able to do things in a reasonable way for larger instances. So just to illustrate, if n were 100, then that basically 2 to the 100 is approximately 10 to the 33rd, and that's more than the universe's atoms, so there is absolutely no hope that you're going to be able to solve that for n is equal to 100. Now, let's look at a particular problem called bin packing. This is a deceptively simple problem. You have items of sizes A1 through AN. You have n items. Each item is of a certain size. We're assuming that AI is between 0 and 1. The two extremes excluded because, well, if it's of size 0, then it doesn't require any space, and if it's of size 1, then it simplifies things. We can just throw these out because basically the task that we're giving ourselves is to take these items, n items of size A1 through AN, and we want to put them into bins. Bins are of size 1. So if an item is of size 1, then it obviously occupies that bin and nothing else can possibly be put into that bin, and therefore those items are completely uninteresting. We just throw them out. The same thing for items of size 0. Well, that's why we exclude 0 and 1 and concentrate on AI between 0 and 1. And so bin packing then simply asks, what is the minimum number of bins? To accommodate A1 through AN, these n items of size A1 through AN. That's the question, and that's what bin packing solves. Bin packing is a nasty problem. It requires exponential time. It's an NP-complete problem. So we have to talk a little bit about what is P, what is NP. P is easy. This is the set of all algorithms that run in polynomial time. No big deal. NP is much weirder. This is basically non-deterministic polynomial time. What does non-deterministic mean? Well, non-deterministic means that you have an oracle that is always right. And so that's where the non-determinism comes in. And once you have that oracle, then you can do things in polynomial time. The problem is, of course, that that doesn't really give you an algorithm because we don't have oracles in algorithms. Algorithms are deterministic. And so that is a kind of weird wrinkle. So basically, if we have all possible algorithms, then there are, well, let's forget about all algorithms. So there's NP, and there is P. Intuitively, we would expect that the non-determinism, the availability of that infallible oracle is going to add something to our ability. So NP probably is more general than P. Obviously, anything that is in P is also in NP, so that inclusion is obvious. The question is, however, what about how do P and NP relate to each other? Are they the same? There are two possibilities. Either they're equal, or P is strictly contained in NP. And this is probably the most famous problem, unsolved problem, in theory, computational complexity. People have been studying that for at least 50 years, and we're really not any closer to being able to answer whether that is true or not than we were 50 years ago. The question still is open, and it probably will stay open for quite a while. Now, what is NP complete? If you have an algorithm that runs in non-deterministic polynomial time, so is an algorithm in NP, then an NP complete algorithm is, in some sense, a hardest algorithm in NP. I'm not making it very formal. Hardest algorithm in NP. What do I mean by that? Well, I mean by that if you had an algorithm that is NP complete, and you found a way of solving that algorithm in polynomial time, then that would give you a polynomial time algorithm for all algorithms in NP. So in that sense, it is a hardest algorithm in NP. If you can find a polynomial time algorithm for an NP complete problem, you have basically shown that P is equal to NP. And as I always facetiously suggest, if you can show that, you can get an endowed chair in any university in the world of your choosing. But don't waste your time. People have been laboring on that problem for, as I said, 50 years, and we're not really anywhere near to solving it. But that's what NP completeness is. It's essentially a hardest problem in NP, and if you can solve an NP complete problem in polynomial time, you've basically shown that P is equal to NP.
Professor, I have a question.
Yes.
All right, so with the NP complete and the NP, how would it actually look like for an NP complete to be P? I mean, I know that we don't actually have the answer yet, but what would it look like? Or, I mean, is there...
You would have to come up with remember, we're talking about problems. So if you have a problem that is in NP, and that is NP complete, then you would have to find an algorithm that does it in polynomial time, solves it in polynomial time. If you can do that, it's over. It's easy to say, it's hard to do. So if you, well, let's just take bin packing. Bin packing happens to be NP complete. Okay, so if you could find an algorithm that solved bin packing in polynomial time, you would now have shown that P is equal to NP. Does that clarify it?
Yes.
Okay. So, now the one takeaway that I want you to have from today's lecture is question optimality. There is optimality, and there is what I would call good enough. Now, of course, you have been, I would say, misled into believing that optimality is what you should be concentrating on. I want to argue the opposite. I want to argue that good enough in many cases is preferable. Why do I say that? Well, let me give you an example. Suppose you want to go from A to B. Driving instructions. And suppose you have an answer. The answer, there are two answers, two parts to the answer. The first part is, yes, I can tell you the optimal way to get from A to B, but it will take 5 hours to compute that answer. The second part is, on the other hand, if you are willing to accept an answer that is off by no more than 20%, I can give you an answer in 10 seconds. Now, depending on what the situation is, if you want to go there and you're being told that with an error of 20%, it will take 4 hours versus getting it optimal, but it will take 5 hours to actually get the answer, which of those two answers would you probably settle for?
The optimal.
You want the optimal. You are going to wait longer than the person who drives there with the not so optimal needs to get there. All right, if you stick to that, let me give you a different example. Finding a spouse. Suppose you are picking a spouse of the opposite gender. There are over 3 billion possible candidates. Are you going to do a complete search? I don't think so. You're not going to go for optimality, because if you go for optimality, you would have to inspect all 3 billion plus possibilities. You're going to go for good enough. Everybody, in practical terms, will go for good enough, because optimality is, in many cases, prohibitive. And that is exactly what is happening for bin packing. Bin packing is going to be something like 2 to the n. Not quite, but close enough. It's up exponential. If I want to solve this, what is the minimum number of bins of size 1 that accommodates an arbitrary sequence of n numbers between 0 and 1? That will require exponential time. That will be optimal. So optimality is very, very expensive, because it is an NP-complete problem. Now, I can do something else. I can say, okay, I'm going to do what is known as descending first fit. So what happens here is that I have an instance of bin packing, which is, of course, a sequence of n numbers between 0 and 1. And so I have a number of bins required by optimal. So I calculate, if I run this optimal algorithm, which of course this is a hypothetical case, because obviously if n is 1,000, the universe will long have terminated before that algorithm comes to an end. But theoretically, there is an optimal number of bins that this particular instance is going to require. See, the fundamental problem with this bin packing is that, yes, you can come up with an answer. I can do it with 500 bins, but that doesn't mean that you know that that is actually optimal. There may be a better way of doing it with 497. And so the question then is, what is the optimal number of bins that I need? And I denote that by opt, I, for I, an instance of bin packing. And now I have an algorithm, descending first fit. First fit. What we do in this case is we're given these numbers a1 through an, and then we sort them descendingly. So we have now a1 prime greater or equal to a2 prime greater or equal to a3 prime greater or equal to, etc., down to the smallest one, an prime. So the prime basically is a permutation of the original ones, and so a1 prime is the largest of those in numbers, and a2 prime is the second largest, and so on until an prime, the smallest of these n a's. And now what we're going to do is we're going to take the first of these and put it into a bin. Obviously, it has to be put into one. We haven't used any bins so far, so the first element, the a1 prime goes into first bin. And then we do the a2 prime. Now, the a2 prime could go into the first bin if it fits. So that would mean a1 prime plus a2 prime is less than or equal to 1. If that's the case, we're going to stick a2 prime together with a1 prime. If it doesn't, then we start a new bin for a2 prime. And then, in general, we have a number of bins filled that way up, and now we're looking at ai prime. And so we try the first bin. Does it fit together with it? No. We try the second bin. Does it fit together with whatever is there? Yes, we put it there. No, we go to the third, and so on and so forth. Eventually, we either find a bin where we can stick it in, or if all of that fails, we have to start a new bin for ai prime. That is basically the process for descending first fit. Now, the algorithm for that is, well, we have to sort. So there are n things we have to sort, n log n for sorting. And then that process of putting things in and testing things, whether we can stick another item together with it, that clearly requires order of n squared. Because if you assume that they're all 0.999, then we need to put it in the first one, and then the second one, well, we have to start a second one, and then the third one, we try the first one, try the second one, and then we start the third one, and so on. So clearly, we have, for the last one, we have to try out all n-1 bins before we start with the nth bin for the last one in this case. So that will take order of n squared. And so if we add that up, then descending first fit runs in time order of n squared. And now comes the important observation. The important observation is that if I have any instance, arbitrary instance, of bin packing, which is a bunch of numbers, A1 through AN, then the number of bins that this descending first fit algorithm, which runs in time n squared, as opposed to optimal, which runs in exponential time, the number of bins that descending first fit requires, in the worst case, is no more than 11/9 times optimal plus 4. So what does that mean? That means effectively that, ignoring the plus 4, which sort of is just a constant addend, the crucial point here is this constant 11/9. Now, if this were 9/9, then that would be 1, and that would mean that descending first fit would basically be optimal. This says this is 22% more. So if you're willing to accept that that the number of bins that you ultimately end up with is no more than 22% more than optimal, then you can actually do that in time that is perfectly acceptable even for very large numbers of n. So even if you had 100,000 or 1,000,000 if n were 1,000,000, well, that's order of n squared. There is obviously no way that you could possibly do that with the optimal algorithm, but you are guaranteed, and I'm not proving that, but it's not very difficult to actually show this bound, you are guaranteed that the number of bins that you end up with descending first fit is no more than 22% more than what you would need for optimal. So that means that at this point we have here a method that allows us to determine a good enough solution in a very reasonable amount of time. And if there's any takeaway from today's lecture, as I said, it should be that you should always question optimality. Now, of course, depends on the context. If you're supposed to sort in numbers, well, either they're sorted or they're not sorted. You can't just say, well, it's not sorted, but it's good enough for me. So many of the problems that you've been exposed to are really, in that sense, binary. Either they're a solution or they're not. And so optimality really isn't that much of an issue. But when you come up with how do I get there, say from A to B, then it may well be perfectly acceptable that your path, your way is perhaps up to 22% longer, but you can get an answer very, very quickly, as opposed to an optimal answer, which of course will be optimal, but it may take you 2 years to get an answer. Now, this is of course an upper bound. There is absolutely nothing that says descending first fit might not give you actually the optimal solution. But what is important here is that you are guaranteed, no matter how things go wrong, that you will never need more than 22% more bins than would be required by optimal. Now, not all NP-complete problems have this property. So if you have a general problem, you have optimal, and you have some other way, some heuristic. For that problem, so problem P, heuristic P, I, and instance optimal. There are problems P for which you cannot find a constant here. This here, of course, is a constant. We can ignore that +4 because it really doesn't, asymptotically, it means nothing. It vanishes. The important thing is that constant 11/9. There are problems, NP-complete problems, for which you won't be able to find a constant. The crucial issue here is, of course, that this is a constant. It doesn't depend on the problem size. It doesn't depend on n. In some problems, NP-complete problems, this will depend on n, and that, of course, then makes it a lot harder to make the argument that that is good enough. If you can say that something is within a fixed percentage more of optimal, then most people will probably argue that that is good enough. If that percentage increases with the size of the problem, then that may well not be acceptable for people. So that is a bit of a problem, because not all NP-complete problems have that property. But if you have an NP-complete problem where you can come up with a constant of within a constant of optimality, then it usually is a good idea to solve that with an efficient, fast algorithm that may not be optimal, but given this definition, is going to be good enough. So that basically is what I wanted to talk about. That is the last topic to be covered in this course. And now, if you have any questions, I'll be open for questions.
Hey, Professor?
Yes?
I've sent 2 follow-up emails and still have not heard anything back regarding my exam 1 regrade.
Send me another email and I'll send a reminder.
So just to make sure I'm sending it to the right place, that's the UH.
No. That has long been discontinued. UHCSEL@gmail.com.
One more time, please.
UHCSEL el@gmail.com.
All right.
So the exam, somebody, I guess, asked a question about the exam. I believe the exam is on the 4th from 2 to 5. I will send out more information. The exam is going to be administered exactly the same way as exam 2. You'll get the questions. You have a certain amount of time that is more than what you would have had in class. And then you have to send that in to the same, to a different account, because we're having two different exams. I'm not going to give you the same exam questions for both sections. So please pay attention to the email that I'm sending you, because it will be different between the two sections. And make sure that you include everything that you want us to look at. If you don't, we will not be able to accept additional material. If you don't send, whatever you send us, we'll take. Whatever you don't send us, we can't take, and not anything afterwards. And make sure that you get a confirmation. If you don't get a confirmation within 2 or 3 minutes, send it again. You do need a confirmation. If you don't get a confirmation, you're not going to, we don't have your exam answers, and therefore you're going to get 0. So don't assume just because you sent it, we got it. If you don't get a confirmation, we didn't get it.
Professor, I have 2 questions.
Yes?
The first question is on exam 2. We saw, at least some people were noting that the people from, I guess somebody was grading, there were 2 different graders, and it seems like the grading disparity on question number 1 was actually really big between class 230 and then class 4. Is this a valid thing to look into, or is it up to the discretion of the grader? Are they using some kind of grading criteria?
If you think that there's a big difference, then just send me an email and I'll pass it on.
Okay, and as opposed to the final exam, is there anything that you would recommend us to do to have a more successful exam?
Well, there's no question that the majority of the questions will be similar to what you had in exam 1 and 2. So I would certainly study those questions and make sure that I understand everything.
Okay, thank you very much.
You're welcome. Now, you do realize, I repeat that, the grades will be posted, I presume, by the 11th, and then you have a week to determine whether you want to stick with the letter grade that was posted, or whether you want to go with the S option that the university created for this semester. The S is basically a passing grade, and it will be considered passing for all purposes, including taking subsequent courses. So you have basically on the 11th, you will get your letter grade, and if you don't do anything, that will be the grade that is going to be on your transcript. On the other hand, by the 18th, you can choose to go with the other option, in which case you will have an S on the transcript. Or, if it's failed and there's no no credit, but basically won't count towards GPA. Yes? What was question one? um, Well, I don't have the questions and I can't really dig it up right now, but essentially what you have to do is you have to determine uh, each element, each array element appears in a page, and that page has to be present in the active memory set before it can be used. And there are two ways of using it. You can either read or you can write. And so what you have to determine is what page a particular array element resides in, and if that page is in active memory set or not. And if it is not, then it has to be fetched. And if the active memory set is full, which usually it is, this is only at the beginning that it is not, then you have to get rid of another page first. And if that page happens to be dirty, then you have to write it back. If it is not dirty, in other words, it wasn't written, it doesn't have to be written back, so you can just overwrite it. So in that case, you can save yourself the page write to external memory, but I really don't have the question. Sorry. Anything else? I can't see any screen. What screen? You can't change my screen. I don't really have any. Oh, okay. Okay. All right. So you have AIJ is HAI. So at that point it flips. Basically the AIJ is you have in column major. Does everybody see what he's putting up there?
Yes.
Okay.
Yes.
All right, just making sure that I'm not talking and you have no idea what I'm talking about. All right, so you have AIJ is HAI times B512 minus I plus 1J. So that B is basically, we're going backwards from the bottom to the top. The B really, this is a bit of a red herring. The B basically is as if it were IJ, except from bottom to top rather than top to bottom. The AIJ, that of course is a row axis. The HAI is a column axis. So J from 1 to 512. This HAI is, what's this? Page size is 256. So you basically need 2 pages for the HAI. You need, of course, 1 page for every AIJ, because these are different pages if it is in column major. So you need for J, for fixed I from 1 to 512, you need 512 pages for AIJ, and for HAI you need 2 because this page size is 256, and for the B you need same thing as for A. So this is 512, and this is 512, and this is 2, so you have 1,026 pages, and then you need that I from 512, so this is 1,026 times 512. That's offhand what I would think is the number of pages that you need. Okay? So where is it now? Come on. It disappeared. Well, I need it. I mean, I can't have my presentation up and yours as well. Okay.
It's also written in the comments.
Well, so we have HAI times B 512 minus I plus 1J. So if I do J from 1 to 512, then this is in column major, so this is the row for given I, J from 1 to 512. So we need a new page for every one, so this is 512 pages. And this is 2 pages, and this is 512 pages. So for a specific I, we need 1,026 pages. And so for all I's, this is from 1 to 512. So we need 512 times 1,026 pages that have to be moved around. So now we have to figure out what has to be written. Well, the A's have to be written, the B's don't have to be written, the B's are only read, and so you can make that determination. But basically the number of pages that are being moved around is 512 times 1,026, so this is whatever it is. Okay? Any other questions? then the only other thing I have to want to mention is teaching evaluations are up, so by all means fill them out, and good luck with your exam.
All right, thank you, Professor.
Thank you. Bye-bye.